All right, so this is the ACS final exam review for Chem 222. We're going to be going through some what are referred to as ACS style problems from your textbook. So I'm going to share my screen here, and let's see if I can share my screen. Oh, there we go. All right, so I'm going to begin here with chapter 7, just to kind of review the style of problems that you may see on the exam. And the exam will be 1 hour and 50 minutes, so a total of 110 minutes, all multiple choice style questions. And our first, let's see here, where's our first ACS style problem? So it's down at the bottom here. Sorry, guys. Multiple tabs open, multiple screen shares, things get messy. All right, so I'll start with 780 here because 779 is not displaying, right? So we have here our reaction. So we have Br on this alkyl halide here, and it's going to react with sodium hydroxide. So what we see here is a secondary alkyl halide. So we should know our substrate. We should also know that hydroxide can function as both a nucleophile and a base. So when we have our secondary substrate here and we're predicting a product, we should think that D would be our correct answer here. And we'll review some reasons why. So A shows the substitution product, which is going to be the major product for a primary substrate, but a minor product for a secondary substrate. Hopefully these words sound familiar from Orgo 1 to you, because we'll still see some of these reactions in synthesis. Then we have, so that's why A is wrong, because it's the minor product. B shows what would be a Hoffman product. So again, another possible minor product, but not the main product of an elimination with a non-bulky base, a small base like hydroxide here. So the Hoffman product implies, if you remember, tert butoxide, for example, would be a bulky base that could produce this less highly substituted product for B, but that's why, again, B is wrong. C, this shows it's also a Zaitsev product like D, but this is the less stable thermodynamically. The form C here, this is the cis alkene, even though it is also di-substituted like the trans alkene we see in D here. We should note that due to steric hindrance, just sterics in general, the trans isomer here is going to be our most stable product. All right, so that's the type of problem solving that I'll walk you through here. So let's see here. We can do 81 together as well. Now we have butene. So we want to synthesize this. We want to synthesize 1 butene, and we're given a primary alkyl halide, a secondary alcohol, a primary alcohol, and then a secondary tosylate here. So the most efficient synthesis means the one in the least amount of steps. So all the problems that you see regarding synthesis on the exam will generally be 1 step, maybe a 2 step maximum. They're not going to be, 10-step syntheses because those problems take quite some time. So in this case here, if we looked at answer choice D, this would provide our most efficient synthesis. Oh, I'm sorry. So 81 is C. I apologize, not D. So what we see here, we need the Hoffman product because 1 butene, if we drew it out, we would see something like this, 1, 2, 3, 4, with between carbons 1 and 2. like so here. We have that pi bond, so we need the Hofmann product. So what happens here with this primary alcohol, we would convert it to a tosylate using tosyl chloride and pyridium here. And this will convert it to a tosylate first, and then that's a good leaving group. So once that is converted, the leaving group's gone, and we use tert butoxide here to form the Hofmann product. So again, these are the types of questions you might see, more simplistic synthesis than maybe on our last exam. You may also see questions that ask you about favorability of a reaction. Oh, oh no, I forgot that it will leave my notations here as I scroll. So let's see. Mm, it will take me too long to erase all this. So I'll just peer through number 82 here. And sometimes we're asked about what is not favorable or some questions about conditions of reactions. So what's not favorable for an SN2 reaction? Don't pay attention to my notations next door there. That's not for that problem. So 82, um, if we had increased steric hindrance in D here, that's an unfavorable condition for an SN2 reaction because we know that we need to have a leaving group leave at the same time that we have a nucleophilic attack. So a leaving group on a primary carbon atom, that's a good condition for SN2. So primary and secondary substrates with leaving groups on the primary or secondary carbons. A polar aprotic solvent. If you recall, way back when, chapter 7, we talked about polar protic solvents. So those that have hydrogen bonding capabilities, those would stabilize carbocation intermediates. So polar protic are favorable for SN1, but in this case, polar aprotic would be favorable for SN2. So that's why A and B are both not correct because they are favorable. And a strong nucleophile, if you recall, SN1 uses weak nucleophiles without permanent charge, such as water or ethanol, methanol. So they're still nucleophiles. They can perform SN1 reactions, but we generally need a stronger nucleophile. So a strong nucleophile has a permanent charge like OH, ethoxide, methoxide, things of that nature. So again, answer choice D, the increase in steric hindrance will be unfavorable for an SN2 reaction. All right, let me just stop share real quick. I'm going to come out to check here. I don't see any chat messages, right? Let me go into chat. Okay, all right, so still all clear. All right, let me go back here. All right, hey Tony. So it looks like more have joined. Good morning. So if you're just joining, I'm gonna go back to some ACS style review questions. This is recording, so just a friendly reminder. Oh, good. And that clears my annotation. So we'll do maybe one more here. How about 786 here? So this we see. We want to know what's the best reagent to achieve this transformation. So if you notice here, our substrate is a tertiary alkyl halide. So this cyclic structure, but the bromine here is connected to a carbon that's connected to 3 carbons. So this is again a tertiary substrate. For this reaction here, we want to know what's our best reagent to accomplish this product here. So this is the Hofmann elimination product. It is the least highly substituted alkene that could result. The Zaitsev product, if we had a non-bulky base, would form inside the ring. So we would want to use a bulky base like tert butoxide potassium. All right, so I would recommend if you want more practice in chapter 7, there are these ACS style practice problems again at the end of the chapter. So I'm going to navigate now to chapter 11. So after our chapter on nucleophilic substitution and elimination, chapter 7. We're going to now look at chapter 11 on synthesis. and those ACS style problems here as well. All right, so let me get a nice view here before everybody joins. All right, so let me go to screen share. And again, this will be chapter 11 on synthesis. And where are you, screen share? There you are. Okay. Um, so let's take a look at this first problem here. Let me move my cameras. So 1126, we're asked here to find the best reagents to accomplish this transformation. So this is almost like what we just saw previously, where we have this alkyl halide, we have an elimination product, but we should always confirm whether or not we had a change in the carbon skeleton, and then did we have a change in our functional group, location, or identity. So let me count my number of carbons here. I have 1, 2, 3, 4, 1, 2, 3. Oh, there's 4, and then I have 5, 6. So I've added on 2 carbons. So at this point here, I must have used a way to extend that. So let's see here. So if I chose answer choice C, this sodium acetylide here, that would do a substitution reaction, right? And we would add on rather to our carbon chain. This bromine would leave, and we would add on those 2 carbons. Again, using that sodium acetylide, this CC triple bond group here. And then since we don't want to fully reduce this to an alkane, we wouldn't use H2 and platinum catalyst, but we could use H2 and Lindlar's catalyst. This was back in chapter 8. You would have seen this, where we end up with an alkene product instead of fully hydrogenating to an alkane. All right. So again, I'll keep an eye out for any questions. Let me scoot down here to 27. Oh, whoa, whoa. Sorry, we lost ourselves here. Actually, let me just stop share for a second, reshare so my notations are gone. Okay. Nope, I'm going the wrong way. So, all right, I'll just pick another question that I can get in view here. How about we do 31 here? So we're asked which reaction sequence best accomplishes this given transformation. So again, we're looking for a transformation here from an alkyl halide to an alcohol. Notice this is a tertiary alkyl bromide, and then we have a primary alcohol as our product. So if we were to follow, let's see here, pathway B here. So say I take this alkyl halide, I subject it to tert butoxide potassium. I'm going to get, ooh, that's supposed to be my Hoffman product there. That should be 5 carbons in the ring. So we can see that my elimination has occurred outside the ring because I use that bulky base. And then if I want to add onto that an alcohol at this position, at the less substituted position, I'm going to need hydroboration oxidation or another anti-Markovnikov hydration. So we would end up with our preferred product there, with our alcohol adding there, our hydroxide rather, and then the hydrogen would add here. So keep in mind those addition reagents from chapters 8 and 9 for both alkenes in chapter 8, alkynes in chapter 9. Those will come back again and again. And while I have us here, let's look at 1132 as well. And we want to know which of these represents a logical retrosynthesis. So we didn't do too much retrosynthesis, but we can work backwards. So we're given this diol target molecule. So that's our product whenever we're referring to a target molecule, and we're going to work backwards. So in this case, we're going to work backwards. We're going to assume that our correct answer choice is A. And let me see if I can walk us through. So we could prepare this vicinal, so a diol here, vicinal diol with two hydroxyl groups on neighboring carbons here. So this can be prepared from an alkene with our transalkene here. Um, and that would prepare this vicinal diol. So all of these other substrates, we couldn't get to this diol. So the diol is the same, but here, besides route C, we wouldn't be able to progress. So I'm going to eliminate B and D here in my retrosynthetic analysis because I do not know any functional groups looking like B or D that would allow me to get to that diol. So now I'm down to just A and C. And I know that if I had a an alkyne here, I could convert that to a transalkene. In C, there's not enough carbons here, and we don't have a triple bond as well. So I would eventually eliminate answer choice C during my retrosynthetic analysis. And we would have to start from the same starting material here. So this implies that we did an addition. So I would have added maybe to my transalkene here, or rather in the correct answer choice, I would have added on maybe methyl iodide or something because I needed to add that one carbon here. So there's a lot of assumptions, a lot of generalizations that we might make. You might just choose whatever reagents you want, but as long as your analysis works, again, we're going to be working backwards, going from the what looks like the product back to the reactant here. And there can be many different scenarios, many different sets of reagents that can get you to that point. So let me step out here so I can clear that writing. Um, no chat messages. All right, so everybody's still just listening. All right, let me do a couple more here from chapter 11. I'll try to get a variety of questions from variety of chapters. And all right, so I'm back in 11. Let's see here. Um, mm, oh, I think that might be, I might be beyond the, let's do 28 maybe. Let's go back here. I think we're beyond the ACS question. So I don't want to give you ones that are not that representative of what we're going to see. So 1128 here. So we're asked which reaction sequence best accomplishes this transformation. So what's our transformation here? So it looks like in not in the same position, but we have a change in functional group here and a change in our carbon skeleton. So I have three, uh, 5 carbons in my longest chain here. And then over here, I have 4. I still have that methyl group on 4, 5, and then an extra carbon here, 6. So what could we have done to accomplish this transformation? So let's see here. So I can go through the reagents. It looks like everything is going to be an anti-Markovnikov addition of H and OH or H and Br. So we have anti-Markovnikov hydroboration oxidation. In C and D, we have anti-Markovnikov addition of HBr. So I'll take us down the correct path here just to save time. So if we added HBr in an anti-Markovnikov fashion, all right, let's see if I can draw that efficiently here. So 1, 2, 3, 4, 5. There's my pi bond. So I'm going to add anti-Markovnikov. So I'm going to add the H here, and then the bromine would be on the end here. So then I'm going to perform this elongation of my carbon chain. So I'm going to add this sodium acetylide here. So I'm going to add on 2 carbons. Notice that my chain is only 1 carbon longer. So what's going to happen is we would extend this. So after the bromine's gone, now we're up to 1, 2, 3, 4, 5, 6, 7 carbons. And for reference, we'll put that methyl group up there. four, five, six, seven. Yep. And now with our oh, rather I should have drawn it this way because it's now going to be a terminal alkyne. So I'm going to treat this with Lindlar's catalyst, and I end up with an alkene intermediate here. And then after ozonolysis, I will end up with this aldehyde functional group on the end. So keep track of your steps. When you have enough space, you'll have a scratch paper to use. So I would draw out each individual step, what your product is after each set of reagents. All right. So far, hopefully the level of rigor for these questions is not too daunting. Um, you will have again all multiple choice, so similar to the midterm exams we've been taking. I'm going to move to chapter 12 now, so we can see a little bit more examples from different chapters. Uh, all right, so 12 ACS style problems. And let me share this. Okay. All right. So let's see. We'll begin here with 53. So we want to know are the best reagents here, or what are the best reagents to perform this transformation? So it seems like the same question over and over again. It kind of is, but now we're talking about taking an alcohol or a diol in this case here and converting it to a ketone and an aldehyde functional group. So let's see here. So if you recall, if we have two hydroxyl groups, one primary and one secondary, our secondary alcohol is going to be oxidized to a ketone. And then my primary alcohol here is going to be oxidized to an aldehyde. I know both of these are oxidized because I've increased my carbon-oxygen bonds from one CO bond to two in the carbonyls. So what reagent can accomplish this? So since I don't want this to be further oxidized, I'm going to use pyridinium chlorochromate. So this is not quite as strong an oxidizing agent as our chromic acid that would form an A here. So again, we don't want that to be oxidized over here to a carboxylic acid. So we're going to use that PCC. So that's a weaker oxidizing agent. All right, let's see. I have 1255 over here in view, so I'm going to move over here. So I'm asked here, what's going to be the major product of this given reaction? So I have a reducing agent here. I have my sodium borohydride, and this will reduce ketones and aldehydes, but not esters. So this group here will be untouched. So what happens is, let's see here, answer choice B will be our correct answer because as mentioned, this reducing agent, it's not the strongest reducing agent, so it will not reduce our esters, but it does reduce ketones and aldehydes. So that's why we see this alcohol functional group, but over here that ester remained. So keep that in mind, the strength of your reducing agents and your oxidizing agents. Let's see here if we can do a Grignard reaction below here. Um, Trying to get to 56. All right. Oh, there we go. Nope. My screen doesn't want to move down. All right, let me see. Where else can I find one? How about 54? So we're asked in question 54 down there, which is not an efficient synthesis of 2-methyl 2-pentanol. So let me grab my oh, my stylus disconnected. Give me a second here. Okay, looks like we have it back up and running here. at least temporarily. So we want to know what's not an efficient synthesis of this 2-methyl 2-pentanol. So let's see here. This is number 54. Um, we want to know, I guess, what will achieve this synthesis. So if I have this reactant here, I have this methyl bromide. This is going to add that methyl group and change this ketone to a hydroxyl group here. So this would accomplish, if we drew it out, 1, 2, 3, 4, 5. So we have 2-methyl, 2-pentanol. So if we flipped molecule A and then subjected it to the Grignard reagent with the acid workup, we would get this product. Let's see what else would give us the right product. Um, B would also give us a correct product here. So now we're going to add on 3 carbons to our chain. 1, 2, 3. So we're going to end up with the right carbon chain here, the correct amount of carbons. This here is going to add on, or I'm sorry, this will change to a hydroxyl group. This is that methyl group at that hydroxyl as well. So far, A, B, and C, it looks like, would also give us our correct answer here. Um, so D is a carboxylic acid, and depending on what substrate you have, a Grignard reagent would not react to form an alcohol. So for this question here, answer choice D would not provide an efficient synthesis, so would not create the product that we desire here. All right, let me remove my writings. I'm going to stop share. Come back, check the chat. All right, we're about halfway through, maybe a little bit more, because I'm going to pause a little earlier than 10 o'clock to ask for any questions. Let's see here. How about, um, I'll give you an example from maybe chapter 13 here. All right. Oh, there we go. Uh, no, it would not. It would not. Aldehydes, ketones, will react with the Grignards. Yeah, so that's kind of like your substrate gives it away in that case. So if you wanted to go back and look at the useful reagent sheets from each chapter, that generally tells you what acceptable substrates you have as well. Good questions. All right. So I'm going to move to chapter 13 in the background here, to those ACS review problems. And again, there's plenty more in your textbook if we don't get through all of them. And you should have access to the solution manual as well. So let's see, what do we have here? 40, 1346. Okay. So, all right, let me share here. Um, let's see here. So our product, we have this given or target molecule is an ether. So in chapter 13, we have ethers, epoxides, sulfides, thiols in this chapter. So this is an ether product. If you recall, that has that general form, ROR. And we're asked which of these methods would successfully prepare this. So we have an R group, which is a phenyl group, and then the other R group. So this is our first R group. This is going to be a tertiary alkyl group here. So we need a tertiary alkyl halide or a phenyl halogen. So the only choice that would work here for this reaction, let's see here. Hmm. If we started, let me see. Hold on. I don't trust my notes here. Hold on. Let's see. The alkyl halide cannot be a tertiary or a phenyl alkyl halide. So what we'll see here is answer choice B would be our only option that could produce this desired product. So I have phenol here, and if I treat this reagent here with this alkene with my mercuric acetate, I'm going to do H and OH addition. So I'm going to have right, my alcohol, my OH portion add over here without rearrangement, my H add over here. And then when I combine this reagent with my phenol here, um, and then reduce my product, this would end up giving me this ether through, if you look up the Williamson ether synthesis. So again, we can't have tertiary or phenyl alkyl halides, so we can use other substrates like alcohols, and we can combine these using a reducing agent here, and this is indicative of the Williamson ether synthesis. So our correct option again is going to be B. We have an alkoxy mercuration that occurs with this reagent here. All right, so I would go back and check out the Williamson ether synthesis from chapter 13 for that product or for that problem. Let me see. Let me just remove my notations, and then what's another good one here? How about 48? What is that asking us here? Um, so we have what products are formed, or which of the following is one of the products formed in this given reaction? So I have my ether here, right? My ROR substrate, and I'm going to add excess HBr, or react it with excess HBr. So the alkyl group, this is going to be cleaved under these conditions. So I'm going to cleave this with the strong acid here with HBr, and going to end up creating phenol as my product. So if you remember, the one product ends up being the alkyl halide, and then on this side, we're going to add that hydrogen. So this is acid hydrolysis of an ether. So we cleave under acidic conditions. So many reactions that you may remember, some you may not. Let's see here. Oh, try to give a representation of each. Oh, how about oh, are these? Nope, that's right before. Mm, we can look at 51 here. All right, so which of these reagents will achieve this transformation? All right, so I have my secondary alcohol substrate here. And what do I need to do? So the alcohol, that's still in the same spot, but I've added on one, two additional carbons here. So something happened. So let's see here. What could have happened? If we use concentrated sulfuric in our first step, so I'm just going to choose the correct pathway here and then walk us through. Mm, think we'll go with B here, because we need to add on 2 carbons. So what happens here, I'll do an elimination using concentrated sulfuric. So I'll end up with this alkene here, so that hydroxyl group's gone. Then I'm going to react with a peroxy acid here. So if you recall, this has this general form here with the extra oxygen in there. So we have this peroxy acid. Oh, actually, I think I drew the R group. All right. or anyway, so sorry. So I'm getting hung up on my drawings, but this is my peroxy acid similar to MCPBA, metachloroperoxybenzoic acid. Regardless of what the peroxy acid is, we're going to end up with an epoxide intermediate here at that site. And when I react that epoxide with ethyl magnesium bromide, so a Grignard reagent in an acid workup, I'm going to open up that ring and I'm going to form my alcohol functional group from the epoxide. And at the same time, I'm going to add on those extra two carbons. So that is why answer choice B would be the best answer here. The others we would convert using PCC to ketones first, and then we wouldn't be able to accomplish that the correct carbon chain in our alcohol. Uh, all right, let me remove those markings. Check back for any questions real quick. All right, and let's move to IR and NMR. So chapters 14 and 15, that was introduced back in Organic 1. There are lots of review materials if you did not cover that in your Orgo 1 course. So I'm going to look at IR next, so infrared spectroscopy. There may be questions on mass spectrometry on the final exam. We're not going to review that this morning. I'm not going to introduce a new topic, but you may see some questions that we just did not cover the content for. That's the same with all standardized tests, the general chemistry exam as well. Classes just don't get to everything that could possibly be on there. So, all right, so I have chapter 14 up in the background. Let me share this with you guys. Nope. Okay, so let's see what we have here. 57 and 63. Okay. All right. So number 57. So we have an IR spectrum here. So you might already notice some signature peaks. So we have one here in the 1700s. Then we have this really wide, broad signal here between I don't know, where does it start? 27 or so, all the way up to 3400. So we could tell here that we probably have a carbonyl, a CO stretch, and then this is indicative of an OH stretch of a carboxylic acid. So if it was an alcohol, it would look like a smooth kind of OH stretch there, not quite as broad as well. So let's see here for 57. Um, Hold on. Again, I don't trust my answer key. Um, Oh, I apologize, guys. So we're asked here so this is the IR spectrum of the product. So I didn't read the question, so don't do what I did. So we have an unknown alcohol. So this is my starting material, and it's treated with chromic acid. So it's going to oxidize fully to a carboxylic acid. So we must have had as our unknown compound a primary alcohol to begin. So this is kind of a retrosynthetic type of analysis. So again, we're going to treat whatever that primary alcohol is with chromic acid. We would fully oxidize that to a carboxylic acid shown here. All right, so let's focus on reading a little better for the next one. Oh, all right, it's easier if I just exit out and then come back in. So we'll do some more practice with IR. And oh, sorry guys, I took you on an adventure here. Okay, here we go. Um, So these are what those mass spec problems might look like. If you want to venture into mass spectrometry territory, that is, recommended. If you think you can just get down the major points, you might be able to get that, one or two problems that you see correct. Let's look at, let's see, 59 here. So now we are asked to identify which of these spectra matches these compounds. So we don't have to do any retrosynthetic analysis or look back here. So we have a narrow signal here around 2100. So this would indicate the presence of a triple bond, either CC, or if we had CN, that could also be a candidate in this region. But looking at our answer choices, that's not the case. So I'm gonna keep moving here. This is 59. What else do we have? We have a signal at 3300. So this is very pronounced. So this is a terminal alkyne CH stretch here at 3300. So all signs are pointing to answer choice D would be our only possible answer. One, I don't have a carbonyl in the 1700s. Um, if I had a CO stretch like these ethers, I would see something around like 1050 here. And I definitely do not see an OH stretch of an alcohol. That's that very recognizable stretch over in the 3000s. So I don't have that either. So hopefully some of these spectral signals are coming back to you. Uh, Let me go out and back in. We'll do maybe one more here in IR and then maybe a couple in NMR and then whatever time we have left, um, we can do some of the later chapters. Let's see here. Okay, so sometimes you're given questions like 62 here. So you're given your substrate. So we have our secondary alcohol, um, and we should have an OH stretch, right? So we're asked here to monitor this reaction using IR spectroscopy here. So we want to know if we've done this transformation fully. So do we have our ketone product here? So if we start with an alcohol, we know that we have that the typical OH stretch, which would be a broad signal in the 32 to 3600 range. So we know that that signal should be there. And then when we convert to a ketone, we expect something around 1700-ish for this carbonyl, maybe a little higher. So we're going to read through the answer choices, and if we looked for the appearance of a signal at 3300 to 36, we'd be looking for an alcohol. So answer choice A is out because that's our reactant, not our product. Um, Answer choice B, not sure where that signal would be. And then this signal should appear, not disappear. So I'm going to eliminate B. In answer choice C, look for the appearance. Again, this is my alcohol, so that's not going to appear, but we have the right signals. So now let's see if we got it right in answer choice D. We're going to look for the appearance of our carbonyl signal, the 1720, and then disappearance of the alcohol. So answer choice D checks all the boxes there. All right. And as usual, I'm moving fast so we can save time. So in the background here, I'm going to jump to NMR questions real quick so we can talk about what they might look like. And then I'll probably pause a few minutes after that. And if you want to ask questions, you can ask me now, or you can send me an email, etc. Um, All right, so I have some ACS style problems from 15 here. So NMR, let's share. Um, there we go. So you should be able to see 1563 here. All right, so this one's ready to review. All right, so if you recall, above each of the signals, that number in red, that will be the number of protons that integrate to give that signal. So remember, if we took the area of each of these signals, so we don't have to integrate them, they'll already be given for us, but this is the term that I'm using, this integration. So 3 protons give rise to this signal with a shift right around 1, right above 1. 2 protons give rise to this shift, etc. So let's look at what compound could be represented here. This is 63. Mm, so if we were to look at the, try to figure out the number of neighbors here. Oh, let me see if I can zoom in. It's not letting me zoom in anymore. Trying to show you guys the multiplicity here. Ah, there we go. So we see this is a triplet in this first signal. So we have 3 protons integrating to a triplet here. And now I have a quartet. So if we went back and looked at our n+1 neighbors, these 2 protons would have 3 neighboring protons. These 3 protons would have 2 because n+1, right? So 2 neighbors. This 1 proton here that integrates all by its lonesome, maybe at 4.6 or so, that would have no neighbors because that's a singlet. And then we have 2 doublets here, so these would imply 1 neighbor each. All right, so that's just a quick review on neighboring protons. So again, you can look to the carbon next door for a neighbor. Oh, it won't let me zoom out now. Hold on, guys. All right, let me back up here. It won't let me zoom back out, so you can't see what I'm talking about as I'm talking about it. Okay. All right, let me come back here. So we reviewed neighbors, we reviewed integration, shift. That's due to deshielding. So when we have a shielded proton, it's going to have a lower shift, more upfield near our TMS. So remember we have that 0 with tetramethylsilane. So let's see, what compound could this be? If we were to draw in our protons here, let's draw in 1, 2, 3, A. And all right, so I have 3 protons with 2 neighbors, so that checks that box here. I have 2 protons with 3 neighbors, that checks that quartet off there. And now I have these 2 protons, which due to symmetry would give a single signal. And either one of these sets of 2 protons could be on my ring. Probably this one here is going to be these 2 because they're closer to that electronegative atom. And then I have this single proton that integrates here. And that makes sense for this hydrogen that's connected to the oxygen. So everything checks out with neighbors, with possible shift. But as a note, you should always look at the multiplicity, so the splitting pattern that tells you how many neighbors you have, and the integration before you consider the shift. The shift is usually a last resort when you're down to 2 compounds that could fit. All right, so let me stop share here. I'm going to actually stop recording.